Hi Geometry. This is our Unit 1 Lesson 15 notes on page 116 of our workbook on symmetry. So let's take a moment and read with me please this paragraph. A shape has symmetry if there's a rigid transformation which creates an image that fits exactly over the original shape. A shape has reflection symmetry if there's a reflection that takes the shape to itself. The line of reflection in this case is called a line of symmetry. A regular hexagon has many lines of symmetry, and here are two. What other lines create a reflection where the image is the same as the original figure? So remember what it means to be a regular hexagon. First of all, it has 6 sides that are all exactly the same length and 6 angles that are all exactly the same degrees. You can have a 6-sided figure where all the sides are different measures, and it would not be a regular hexagon. So let's look at this line of symmetry for a moment. When I fold my hexagon on this line that connects the midpoint of the top to the midpoint of this bottom, when I fold my hexagon on that line, I notice that it lines up perfectly with itself on the other side. Any mismatches, probably my drawing error. So this line of symmetry basically splits my hexagon in half perfectly. They also show in the other hexagon a diagonal line that does this same thing. It goes from vertice to a vertice. My points, where my edges meet, are my vertices. So if I look at that line of symmetry and I fold on my blue line, I see that my hexagon also lines up perfectly. So there's other lines of symmetry. So let's go find our other lines of symmetry in this hexagon. Why don't you pause the video for a moment and see if you can get them all. Welcome back. I hope you join the midpoints of all 3 sides. Well, it's all 6 sides, but it's 3 lines. So I have 3 pink lines in my picture. Those 3 lines of symmetry are the ones joining midpoint to midpoint of each side. So those are joining my midpoint to my midpoint of the opposite side. And then let's take a look at my vertice to vertice. So from this vertice to the opposite vertice, let's do this vertice to the opposite vertice. That splits my hexagon in half. And finally, let's do this vertice to this vertice. It also splits my hexagon perfectly in half. So I have 3 more lines. They're all blue. 3 more lines of symmetry. Those go from vertice to vertice. So it looks like I have 6 lines total. So there are 6 lines of symmetry in my hexagon. That would be my answer. So I want to just point out a common mistake some kids make. They draw all their lines of symmetry great. Then they start at the top and they start counting them. 1, 2, 3, 4, 5, 6. 7, watch what I'm doing here, 8, 9, 10, 11, 12. So in other words, they just keep counting the same line again. When you've started counting this line as your first line of symmetry, that's the other side of that line. So 1, 2, 3, 4, 5, 6 lines of symmetry. And I wouldn't count any of these because they're the other side of the line I've already counted. So just keep that in mind. So let's take a look at an equilateral triangle. So an equilateral triangle has an odd number of sides. And this shape then does not have a vertice to vertice or a midpoint to midpoint line of symmetry. So if we take a look at our equilateral triangle, which is a regular polygon, it has a vertice to midpoint of the other side line of symmetry. So if I trace my triangle on my patty paper, I notice that this line splits my triangle in half. That would be my line of reflection. That's my line of symmetry. That's my line that divides my triangle perfectly in half. There's 2 more in this triangle. I also have a line of symmetry from this vertice to the midpoint of the other side, and from this vertice to the midpoint of the other side. This is not necessarily true of all triangles. This is true of all equilateral triangles, so keep that in mind. So I have 1, 2, 3. There's 3 lines of symmetry in this equilateral triangle. I can split that. So a rectangle is often missed initially by kids because they actually see 4 lines of symmetry, just like a square would have. A square and a rectangle are different. In a rectangle, my opposite sides are congruent, but all 4 sides are not congruent. So often students think there's 4 lines of symmetry in a rectangle. Why don't you pause this video and draw in your lines of symmetry for your rectangle? Be careful. Welcome back. I hope you've drawn in your lines of symmetry. For a rectangle, you have a line of symmetry connecting the midpoint of the top to the midpoint of the bottom. You can see if I fold my rectangle on this line, I've split it in half. You have another one connecting the midpoint of the sides. If I fold it along this dotted line, I also would match up on both sides. However, in a rectangle, there is no vertice to vertice. So sometimes students think that they've got a line of symmetry going through the middle of the rectangle, a diagonal. But let's take a quick look at that, shall we? So let me trace my rectangle and let me fold my rectangle on my diagonal as well as I can. And you'll notice that you'll see one of the points of my rectangle here and the other one is over here, meaning that it is not matching up on top of itself. It doesn't fold over corner to corner. And so there are no diagonal lines of symmetry. So for a rectangle, I would have 2 lines of symmetry. So let's take a look on page 117 at problem number 2 in our practice. So in this practice, they give us this quadrilateral BADC, and they say that AB is congruent or equal to AD. They say that BC is equal to DC, so I've marked those appropriately. And then they say the line AC is a line of symmetry. Well, let's remember what that's meaning. If that's a line of symmetry, it should be also then a line of reflection. Sorry, I'm looking for my straight edge. So let's connect A to C so I can get a visual of that. Line of symmetry, line of reflection. Oh, I can see if I folded the top triangle down on the bottom triangle, they would be matching up. I can visually see that. By the way, this quadrilateral means it has 4 sides. This is called a kite. This is not a rhombus. A kite specifically has 2 congruent sides touching, and the other 2 sides are also congruent and touching, but the 4 sides are not all equal. That would be a rhombus, has all 4 sides equal. So let's take a look at 2A and 2B. In 2A, it says, based on the line of symmetry, explain why diagonals AC and BD are perpendicular. So let's draw in BD to get a visual of what they're asking me. So if I draw in BD, this question A is saying, explain why these should be perpendicular. So I'm thinking back to the fact that my line of symmetry is also my line of reflection. So in this case, these would be perpendicular because my line of symmetry that's my AC, is also the line of reflection. So I know if reflected, B would line up on D. They're equal distance apart. So that would mean that my pink line has to be perpendicular to my line of reflection. Remember, my reflections, when we were constructing them last week, we always constructed the perpendicular line through our point, and then we measured the distance that it was to my line of reflection, and we marked that distance on the other side, and that's where I would reflect it. This would be like my B prime, if you will, last week. So if reflected, B would line up with D. So therefore, I know that AC is perpendicular to BD. Let's take a look at question B. Question B on the same page says, based on the line of symmetry, explain why angles ABC and ADC have the same measure. So let's go find those. A, go to it first, B, C. So I'm talking about this big angle on top, and ADC, this big angle on the bottom. And it says explain why they'd be the same. Well, if I folded triangle ABC over the line of symmetry, it would lay perfectly on triangle ADC. So therefore, angle ABC is equal to angle ADC. So when I notice, when I lay them on top of each other, if I trace this, my patty paper is getting very filled up. Let me see if I have a second one I could use for this. I do. So if I trace my original ABC and I reflect it over, I see that it's matching up perfectly with ADC right here. They line up perfectly with each other. I know they're congruent. I did a reflection and they sit perfectly on top of each other. And so I know that they're congruent or the same size. Remember, if you do a rigid transformation and your original shape lines up on your image, then you know that they are congruent to each other. That's if I do a translation or a rotation, or in this case, I just did a reflection and they lined up perfectly. Therefore, they would be congruent or equal in size. At this point, you can stop the video and you can work on your practice 15. Hi, as I just mentioned, if you want to stop the video, the lesson 15 is over. However, I'm going to take a moment and do a few of practice 15's problems with you. So stop the video, go do your practice 15, and if you run into trouble, come back to this video and I'll be explaining a few of the problems in more detail. So the first problem I'm going to begin with is number 4. This is on page 118. And it's my practice 15, number 4. And it says there's a square ABCS inscribed in a circle with center D. So I'm going to draw that. And I wrote a note to you that this is similar to Unit 1, Lesson 14, number 2, which was on page 108. I believe that was an equilateral triangle. But this is a square, so I'm going to attempt as best I can to sketch a square. I could construct it. I can make this perfectly. We learned how to do that in lesson 7. But I'm just saving a little bit of time here and I'm sketching it. And it was A, and I can go either direction now. I'm just gonna spin around this clockwise, naming all of my vertices in order. It says, what is the smallest angle we can rotate around D so that the image of A is B? In other words, I want A to go to B. I would like A to end up on B. So there's a couple ways to look at this, but essentially what's happening here is this is where A is, and I want to rotate my square in such a way that A is on top of B when I get done with my rotation. How much of a rotation is it to take A to B? So I look at my circle, knowing a circle is 360 degrees all the way around. And basically, because this is a square, I'm dividing my circle into 4 parts. So this would mean that each of these parts going around my circle would be equal to 90 degrees. So this is a 90-degree rotation to take A to B. Another 90 degrees would take A to C. Another 90 degrees would take A to S. And finally, the last 90 degrees, or 360, would bring A all the way back around to itself. So it looks like this answer would be 90 degrees, C. Moving on to page 119, this is really 4 problems in one. I'm going to do the top one with you. Notice I labeled these A, B, C, and D. I don't particularly like to draw lines across my page to match them. I think it looks a little bit messy for me. It's hard for me to keep track of what my answers are. So over here on the right side, I'm basically going to put a letter out to the side, A, B, C, or D, whichever one of the pictures on the left matches the rotation that we're talking about here. There it goes. So the first thing I'm going to do is I'm going to rotate my original POG. I'm going to rotate it 60 degrees clockwise around O. So I'm going to get my patty paper, and I'm going to trace my original POG, P, O, and G, and it's said to do 60 degrees clockwise around O. So I'm going to hold my pen really tightly on O, and 60 degrees clockwise. So I know my direction is the direction of a clock. So I'm going to spin the same way that the clock hands do. So if OP was a clock hand, it's going to be going this direction. And I want to spin it 60 degrees. So I'm going to use my triangles for help there. So if I'm looking through here, if this is blue line is one side of my triangle, I basically want to move that line to the other side of that triangle I can see through my patty paper. That would be 60 degrees because these are equilateral triangles. So each triangle is 60 degrees. That gives you my 360 degrees all the way around O. So I just want to click, if you will, one triangle. So I'm going to take this blue line to the next triangle. So let's do that. I'm going to go across a triangle and stop. All I did is I went from this side of the triangle to this side. I only did one triangle because it's 60 degrees. So it looks like I've kind of got this horizontal GP right here. So I look through my answer choices, and there's 2 of them, both my C and my D. But notice that my C is higher on my page and my D is lower on my graph. So let's go back one more time. I believe it's D. It seemed pretty low before, but let's just double check again now that I've looked more carefully at my answers. So when I rotate this one triangle, it ends up, yep, just 2 triangles up from the bottom. This would be my answer choice D. So I write that off to the side. And then I simply continue doing each of the 4 problems. This is really a 4-problem problem. And when I get done doing 120 degrees clockwise, I will, once I see what that looks like here, I will choose the answer on the left that matches. And then finally, let's take a look at number 6. Number 6 is the last problem assigned on this practice. And it's talking about lines L and M being perpendicular and reflecting a point over line M. So line M is our line of reflection. And this is going back to lesson 11. So you can always look back at practice 11. We did something similar there. But it says sometimes reflecting a point over a line is the same as rotating it by 180 degrees. Using center P, select all label points which have the same image. So back in practice 11, there was a certain location a point had to be where reflecting over my yellow line M and rotating 180 degrees around P was actually had the same image. So A, for instance, when I reflect it over line M, my A prime will be on the other side, the same distance away. So this is my A prime. And coincidentally, if I rotate 180 degrees around P, 360 is a circle. So if I rotate 180, it's half a circle. My A prime is going to end up in the same place. So A is one of my points where reflecting it across my yellow line M and rotating 180 degrees is the same movement. So there's another point where that's true too, and you have to pick it out. Thank you very much for watching some of the practice problems in lesson 15.